Hello everyone, welcome back to our discussion regarding energy, and today we're going to be talking about conservative versus non-conservative forces. So what are conservative forces? Conservative forces are forces which do not depend on the path taken. And what does that mean? What this means is that we have an integral that represents our work. Of course, we saw that from last class. And we know that we go from an initial position to a final position, and then we take the dot product of our force and then dot it with our displacement vectors. But we can also rewrite this in this form right here, where we have an integral with a circle here to represent a path. And in the case of conservative forces, we see that the work is going to be equal to 0. So, what does this mean conceptually? If we take a path from, say, A, we can go like to B, point B, and then we can go for multiple ways. We can go from A to B, and then from B back to A. Or you can go from A to B and then pass through C and then back to A. Or you can go from A to B and then pass through D and then come back to A. And in all these cases, you should find that the work done along this closed path is going to be 0, regardless of whether or not you pass through C, D, or just through this segment right here. And there are various examples of forces that we are going to be considering and have considered in this class, including gravity. You also can have considered forces with ideal springs, and then also with electrostatic forces as well, which we're going to talk about later. We're going to talk about springs later, and then electrostatic forces are more going to be talked about in physics too. And then for non-conserved forces, they're the exact opposite of conserved forces, where these forces do depend on the path taken, and then the work done along the closed path is going to be non-zero in general. And these forces can include, like, say, friction, air resistance, tension, pushes, pulls, etc. And if we take a look at, say, friction, for instance, right, we can have this ground right here, and then we'll put a box right here, and let's suppose we push this box to the right, like this. We know that friction is going to act in the opposite direction of that motion. And if we push the box to the left, you'll see that the friction should be opposite to that direction, which is to the right. So you'll see the displacement vector and then also the friction vector are going to be opposite of each other, regardless of whether or not they're going to be, whether the box is to the right, moving to the right, or to the left. And we can see that friction will dissipate energy in both of its directions. So hypothetically, if the box moved to the right and then back to the left, you expect there to be a decrease in kinetic energy, so you would have less kinetic energy by the work kinetic energy theorem. Now let's take a look at gravity. Let's suppose we have an initial position right here, and then we have our gravitational force, of course. And then let's put a displacement vector and the force vector on a single particle. And let's see how this is going to advance with time. So we have the particle going up to here, force is going to stay the same, and the displacement is going to be going upward. Then you have the force being downward, and then you have a displacement upward, and then eventually you reach the top. But force is still downward. You have your displacement vector going this way. You have your force vector still going downward. And you go frame to frame. You see that your displacement is increasing, and so forth. So you'll see clearly that the gravitational force and also displacement vectors are going to be along the same axis, which is pretty good for the work kinetic energy theorem, that is. But if you were to take a look at projectile motion, in this case over here, you would notice that the projectile is going to start right here, and then the force is going to be downward. You're going to have you're going to have your displacement vector going this way. And if you look at frame by frame, you'll see that the displacement vector tends to decrease in length, especially in the y direction. But the gravitational force is still downward. And then you have your particle still going upward with this displacement vector decreasing in magnitude, and eventually reaches the top like this. And then you have the particle going downward and keep going downward and downward until you reach a final position, just like we saw over here. And our goal here is we want to figure out the work that is done during this trip. So I'm going to put a snapshot right here where we have the force and dr placed such that there's an angle of theta between the two. And if you recall back to scalar products, we know that if we take the force and then a component of dr that is parallel to the force, we can easily calculate the scalar product. So let's use that concept to our advantage here. So this is going to be equal to the force times dr prime, and then we can use the angular form where we have our work is equal to F dot dr, and we know for sure from what we learned a few weeks ago that we have force, the magnitude of force that is, times the magnitude of dr times the cosine of the angle that's formed between the two is going to be equal to our work, and that is the angular form of our dot product. But what we can also see is that we can take dr cosine of theta and notice that that is actually going to be equal to dr prime. And if you take that into account, you'll notice that your work is going to be F times dr prime. So what does this mean? If we take the projections, that is, the vertical components of our displacement vectors for our projectile motion, we'll notice that there's only a dependence on the vertical height for the work. And these projections, these parallel projections that is shown here in purple. So we have an upward arrow for one instance, we have an upward arrow here, and then we have upward arrow here, and then downward, downward, and downward. So this is going to be our motion that we expect to see for one-dimensional motion, that is. And the cool thing is, right, whether you're looking at the particle moving upward, as we saw over here, or you see the particle going in this arc-like fashion like this, you'll see that the work will depend only on the height, whether it's one-dimensional motion or 2D motion. And just to kind of sum this up, we see the work depends only on the parallel component, as we can see over here. And in other words, that parallel component is going to be the vertical height of our displacement vector. And this will form the foundation for potential energy today. So now let's actually figure out how to get this potential energy here and start getting into conservation of energy as well. So how do we find a potential energy? A good place to start would be using our kinematic equation here, just like we did with the work kinetic energy theorem. And if we do the same trick, we'll notice that we can get this form for our energies here. So you can see we get kinetic energy here and kinetic energy here. And the first one that's listed here is going to be the initial kinetic energy, which is shown here. And then you also have the final kinetic energy, which is shown in red over here. But then you might be thinking to yourself, what is up with this term over here? This here is going to be the foundation for our potential energy, U that is. So we take a look at our equation down here, and if we take a very close look at this, if we can rewrite this equation as delta K is equal to negative delta U. This blue part here is going to correspond to our delta K, and this pink part here is going to correspond to our delta U, or minus delta U. And if you rearrange this, you'll find the sum of the change in kinetic energy plus the change in potential energy is going to equal 0. And if you take a real quick close look at this, you'll notice for gravitational potential energy, you'll notice that the delta x will represent the change in height. Now, if we take a look at this in an integral form, we know that work is equal to the change in kinetic energy, and we saw this integral on the previous slide and last class. But if you use this definition right over here, along with this over here, our work kinetic energy theorem that is, or integral I should say, you can clearly see that delta U can be written as the negative of delta K. And you find that delta U is just simply negative this entire integral. And if you wanted to figure out what delta U is going to be for, say, like gravity, you could do negative, integrate from 0 to h, and then you stick in your gravitational force, and then you take the direction that you're working with. In this case, it's the dy. Integrate this out, you get negative mg times y, going from 0 up to h, and you find that your potential energy is going to be mgh. So let's actually take a look and see how we can interpret this conceptually. So we got a force going downward like this in red. We have our ball here, and I'm going to be drawing some frames here that are all equally spaced, as you can see here. And I'm going to be drawing out some levels. So we got y is equal to 0, we got y is equal to h over 2, and then we have y is equal to h. And I'm going to be plotting the potential energy for each level, each height that is. And as you can see here, the potential energy tends to increase as I go from lower up to higher. And as you can see here, the potential energy is 0 here. The potential energy is going to be this length here. And then the potential energy up here is going to be twice as large as this one here. Because, well, this height, h, is twice as large as this height here. And then if we take a look at the speed, you'll see that the speed is going to look something like this by these green arrows. So it's going to be maximum at the bottom. It's going to be somewhere in between in the middle, and it's going to be 0 at the top. Let's take a look at the kinetic energy now. You'll see that kinetic energy is going to be max. That makes sense because 1/2 mv squared. Kinetic energy decreases a bit, and then kinetic energy goes to 0 at the top. And if you were to add these bars together, Ke plus Pe, and then a Ke plus Pe here, and a Ke plus Pe here, you'll notice that the sum of those bars is going to be the same. And just kind of sum it up, the sum of the changes in K and U are indeed going to be 0, as we saw over here at this equation. And what that leads to is that we have the sum of K and U must be constant. And that kind of forms the foundation for conservation of energy. Now let's take a closer look at potential energy in the context of forces. So let's first talk about non-conservative forces. In the case of non-conservative forces, right, you would clearly notice that you'd expect that the initial energy of the system, that is, initial kinetic plus potential energy, is not going to be the same in the final and initial states. And the way we write this is that we have the change in E, change in total energy of the system, is equal to our work of a non-conservative force, as you can see here. And again, we can see clearly that forces that are non-conservative are going to not conserve energy. So that means that EF and EI are going to be different from each other. And in the case of this class, we'll see that friction is going to be the major non-conservative force we're going to be dealing with. But in the case of conservation of energy, we can actually notice that we can write our delta K is equal to the work, where we have work plus our non-conservative work, that is. And in the case where we have no non-conservative force at play, so like for instance we have no friction, we assume that the work due to the non-conservative forces is going to be 0. So we find that work conserved plus 0 is going to be equal to negative delta U, which reduces down to the case that we saw on the previous slide. And then we come down to this equation right here. And if we break apart this equation a bit, right, we'll find that we can write the difference in our kinetic energies plus the difference in our potential energies is all equal to 0. And then if you rearrange that, you'll get this equation right over here, where you get the sum of kinetic plus the potential in the final state is equal to the sum in the initial state. And in the case of this equation right here, assuming that there is a non-conservative force at play, you'll find that you would need to have a non-zero value for your non-conservative work, that is. And just to kind of sum this up, you'll find that total work will incorporate all forces, which will include both conservative forces and non-conservative forces. And then this red box here is there just to highlight those non-conservative forces and the work you'll calculate from those non-conservative forces. Now let's talk about total mechanical energy. So the way we typically represent total mechanical energy is by means of having K plus U is equal to E, and that is all equal to a constant value, where E is going to be equal to a constant value, which means that total mechanical energy is going to be conserved. And then if we go to conservative forces, if we want to kind of tie forces and energy a bit together, what we find is that we can write du is equal to negative F conservative times dx. So what can we do with this? We could rearrange this to solve for our conservative force, which is just going to be negative du over dx. And that's how we get our force from our potential energy. So if we know our potential energy, we can get our force, and vice versa. We can also know our force and also get potential energy as well. So let's see how we can do that. Before we do that, let's expand the three dimensions. So if we had a function of u, where u is equal to some multivariable function, where the potential energy is a function of x, y, and z, and then you also write du as negative the force, the conservative force, divided with dr, you'll find that you can actually write du like this here, where you pretty much have your expansion, or your component form, of your dot product here. You got your force on x times your dx, force on y times dy, and force z times dz, and so forth. And then if you were to rearrange, solve for the force in the x, y, and z direction, you'll find that you get these quantities here. The fx is equal to negative partial derivative of u with respect to x, and you get the same thing for y and z. The only thing that's going to be different is that you're going to be differentiating with respect to y for fy, and then you're going to be differentiating with respect to z for fz. And if we want to kind of try to interpret what the force is going to be from like a potential energy versus position graph, you'd say you take like this bowl-shaped curve here. If you were to take a look at the bottom here, this bottom dotted line, you'd see that du dx over dx, that is equal to 0, and that corresponds to a force of 0. If you take a look over here, the slope is downward, so du dx is less than 0. But remember, there's that negative sign we need to incorporate right over here. and that is going to give us a positive force. And then we have the case over here where we have an upward slope. As you can see, we got du over dx is greater than 0, which corresponds to a force that is less than 0. Now let's take just a little bit of a moment to kind of like try to interpret what's going on here. Imagine this is like maybe some valley, right? And if you had like say your particle here, which is represented as this laser dot here, you would expect that this particle would tend to go this way. And it kind of does make sense that it would go this way from an intuitive perspective. But if we think about it in terms of forces, if we see the particle initially going here, and it's eventually going to want to speed up going down like this, that means we're going to need a positive force to get it to increase its speed, and also to be moving to the right. But if we take a look over here, if we have a particle situated like right here, and then intuitively the particle would want to go down like this, and eventually come down here. Does this make sense in the context of f being less than 0? Yes, it does, because the particle is going to have a tendency to move to the left, which is captured by a force that is pointing to the left. And just to kind of sum things up here, we can see that the value of the conservative force is simply just going to be determined by the slope of the tangent line of this ux versus x curve, but also keep in mind that you also need to incorporate that negative sign as well. Now let's take a look at here an example where we have someone skating up an incline. So what we have here is we have an incline that is situated at an angle of theta, and our goal here is for us to track the potential and kinetic energy as a function of height. We got a height h, we have a length of incline L, and we have a box situated here. And my goal is to track the motion of this box. So what I'm going to do is I'm going to have these free energies here. We have the potential energy, the kinetic, and the total mechanical energy, that is. And I'm going to have my time axis here, and I'm going to see what happens as my box moves up. So I had the box moving from here up to here. And as you can see here, we know that the red curve, as we can see here, is going to be increasing because you're going upwards. You're increasing your vertical height. And then your kinetic energy is going to go down. And this is under the assumption that we have a box that's moving up the incline with some initial speed. Let's call the initial speed v in this case. And then we have our total energy up here, represented by purple. And if we take a look at this as time progresses, we'll see that our potential energy increases, and then our kinetic energy decreases. Keep going. Our potential energy increases, kinetic energy decreases, and by the way, total mechanical energy is remaining the same. And we reach the top, and this is what we get. We get our potential energy maximized, and then we have our kinetic energy minimized down here. And then let's assume that we just kind of just go back down. Assume that this is like a skateboarder going up a ramp and then coming back down. You'll find that you get the symmetric case. So you see that you'll see that your potential energy starts here and then starts going down. Kinetic energy starts going up again. And if we keep following the curve, we get this, and this, and this. One more. There we go. So that's the complete track that this box is following along. And we can see clearly that potential energy is going to increase as, well, H is going to increase. And we can see that kinetic energy is going to be minimum at the top. In fact, I'm going to put that on the diagram. So we see potential energy is 0 at the bottom. We see that kinetic energy is going to be max at the bottom, assuming that there is an initial speed. We see that potential energy is max at the top. And we see that kinetic energy is 0 at the top. And also we see that the total mechanical energy is going to be equal to the sum of the potential plus the kinetic energy, which is indeed going to be a constant. And if we want to figure out the incline length, that is, just from this information, like we know speed and we know the angle, let's see how we can do that. We know our conservation energy condition is this here. And we know our initial kinetic energy is going to be 1/2 mv squared plus 0 is equal to 0 plus mgh. So mgh for our max potential energy, and then we have initial kinetic energy as being 1/2 mv squared because that's what it is at the bottom. And then you get rid of the zeros, you get 1/2 mv squared is equal to mgh. And also keep in mind that h is going to be equal to L sine of theta. That makes sense from trigonometry. And if you were to rearrange this a bit, you'd find that h is going to be equal to v squared over 2g. And then you find that you get L is equal to v squared over 2g sine theta for this case. Now let's take a look at another example problem. We're going to be finding the final speed from a graph. So, just like we did before with the work kinetic energy theorem, we're going to have a graph. In this case, it's going to be potential energy versus position, though. And I'm going to have potential energy on the y-axis, of course, and then I'm going to have position over here on the x-axis. And my goal is for me to figure out some things about this box over here. Where this box has a mass of 2 kilograms, and this box can be moving from -5 meters all the way over to 4 meters, and it's going to have an initial velocity of 2.5 meters per second, and our goal is to find the force at x is equal to -3 meters, and also the speed at x is equal to 2 meters. So let's see how we can do this. So first things first, let us outline the region that we need to find the slope of for us to be able to figure out the force. And that's going to be represented by blue here. And then we get our force is equal to negative the change in u over the change in x. And that's equal to negative the change in your potential energy. That's 3 joules minus 0 joules. And then you divide by -2 meters minus -5 meters. And then you'll get this equal to -1.0 newtons. And that is going to be your force. But if we're taking a look at the speed, this is a little bit of a different story. And a good place to start is for us to look at the work kinetic energy theorem and how that's related to a potential energy. So work is equal to change in kinetic energy is equal to minus delta U, of course, and that's also equal to the change in U. That's initial U minus the final U. And if we recall from last class, we got speed is going to be equal to the initial speed squared plus 2w over m. But I'm going to make a little bit of a change here. Instead of taking w, which is the change in kinetic energy, I'm going to take advantage of the fact that I know that the change in kinetic energy is equal to negative the change in u, and stick that right into this formula. And we can see clearly that we get a minus sign right here. And then what we want to do is we actually want to find the change in u, that is. So we go from here, I, that's our initial position, and then we go to our final position right over here. That's what we're going to get. We have our initial position here and final position here. And we can easily figure out the change in the potential energy this time. And keep in mind, we are not going to be integrating this time. We're going to be taking the difference between our final potential energy and our initial potential energy here. And if we do that, we'll get 3 joules. So stick that right in there. That means that our final speed is going to become the square root of 2.5 squared minus 2 times 3 over 2. And that is going to give us 1.8 meters per second as our speed at this position right here at x is equal to 2 meters. All right, now let's take a look at one last example. We're going to be taking a look at a mass that is going to be going up an incline, but this time with friction. So let's suppose we got a mass, call it m, and it starts at point x, and then eventually we want it to get up to point q. So let us take a look and see how we can model this problem. First thing we're going to do is we want to put the forces that are going to be on this mass, which include the gravitational force, and you also have the normal force, and you have the frictional force. So hopefully you know how to do this with setting up your net forces. So in the y direction, you have n minus mg cosine of theta is equal to 0, and that turns out to be n is equal to mg cosine. You have the net force in the x direction. That is going to be your minus friction force minus mg sine of theta, and that is equal to, when sticking in your normal force, you get minus mu k mg cosine minus mg sine of theta. And if you were to factor out the mg, minus mg that is, you'll find that you get minus mg times the quantity sine of theta plus mu k cosine of theta. And that is going to be our force in the x direction, net force that is. And then we can also use the work kinetic energy theorem for us to be able to figure out the speed. So let's take a look here. We have the work is equal to change in kinetic energy, and we know we take our final kinetic energy minus our initial kinetic energy, and that is going to be equal to our force dotted with our displacement. And in this case, we know that we're going to be dealing with a mass that's going to be moving up the incline like this. And then you also have a distance that you're going to go along the incline. So from here up to here, that is going to turn out to be h over the sine of theta. And then if you stick this in as your fx net into here, multiply by your h over sine of theta, and do all that math out, you'll get negative mgh times the quantity 1 plus mu k over tangent of theta. And then if you set this quantity equal to this quantity here, you'll find that your final speed will turn out to be this expression right here. But that's using the work kinetic energy theorem. That's old news. Let's work with conservation of energy. And yeah, that's speed at the top of the incline. So conservation of energy time. You have the kinetic energy at the bottom plus the potential energy at the bottom is equal to the kinetic energy at the top plus potential energy at the top plus the work due to friction. Now this is where we're going to be considering a non-conservative force now, which is of course friction. We know at the bottom of our ramp that we're going to have an initial speed of 1/2 mv naught squared, and then we're also going to be adding in the potential energy, but we can assume that the potential energy is going to be 0 at the bottom, and we set that equal to 1/2 mv squared, and that is going to give us our final kinetic energy, and then we have plus mgh, because that's our potential energy once we reach point Q. And then we also have this term here, where we have mu k n times our h sine of theta. This here is going to be the work due to friction. You got your friction force, mu k n, and then you have your distance as well. And if you were to rearrange this out, and also consider the normal force, mg cosine of theta, you would find that this whole equation can reduce down to v squared is equal to v naught squared minus 2g minus 2 mu kg cosine times h over sine. And then, if you were to take this equation and reduce it such that you're able to get just v alone, you'll get your final equation as v is equal to the square root of v naught squared minus 2gh times quantity of 1 plus mu k over tangent of theta. And you can see clearly that this expression here is equal to this expression right here.